in terms of equation itself, and these conditions guarantee or indicate integrability of the given PDE. In this talk, integrability equation is considered to be integrable if it admits Lex representation. There is a number of
arbitrary or with a parameter.
I'll discuss later. Well, there is a number of interrelated but not non-equivalent definitions of integrability. Well, I will use this definition. Equation is integrable if and only if it admits Lex representation. Actually, all examples today will be integrable in this sense, but not integrable in perhaps some other in some other senses. And well, I would like to omit this discussion during this talk. Well, in a number of my previous talks, I discussed the approach based on the twisted extensions of symmetry algebras. Unfortunately, and as I have mentioned before, this approach is not universal. There are examples of equations which do admit Lex representations, but whose integrability can't be detected using the technique of twisted extensions of symmetry algebras. Today, I would like to present some generalization, some perhaps development of this approach based on the notion of Lie-Rinehart algebras. And I hope this, I would like to show that this approach extends the class of equations whose integrability can be detected by this technique. Well, to start, let me recall the basic definitions and the technique of twisted extensions. Well, we have an equation, PDE, partial differential equation. Well, then Lex representation is understood as a system of equations. Some you are differentiated with respect to xk is a function of x, u, its derivatives, and this fiber variables that are called sometimes pseudopotentials. Well, it is supposed that A and B may be the number of these fiber variables can be infinite. And the requirement is the following: the cross differentiation of this system this equation is compatible. We substitute right-hand sides into this expression, and the cross differentiation gives the same results if and only if the initial equation is satisfied. The right-hand sides perhaps depend on some unremovable parameters, but it's not so important for today's talk. In other words, we can reformulate this condition using the notion of Walquist-Estabrooke forms. Let's consider the following forms. Okay, some for k, t, a, k, dxk. Then this condition can be reformulated in the following manner. The exterior differential of this form can be expressed in the following way. Some form B and some forms, two forms omega capital, and these forms are equal to 0 whenever initial equation is satisfied. Well, this equation at least sometimes it is possible to define the LX representation using just one form, just one Walk-Testable form. And then in this situation, this equation can be written as follows. Okay. Well, and inspired the fact that this equation looks like the equation for a twisted extension of Lie algebra, I have proposed the technique based on these twisted extensions. Let me recall the example. Let's consider the following equation. It's a hyper CR equation for Einstein-Weyl structures. Well, this equation was shown to be integrable independently by Mikhailov, Dunayski, and Pavlov. How to? I would like to recall how to detect integrability using the technique of twisted extensions of symmetry algebras. We consider the symmetry algebra of this equation, and it's the structure equations of this symmetry algebra. They appear to have the following form. The theta capital is equal to, okay, sorry. Plus something like this, correct, quadrant. Where theta capital is actually an infinite series of one forms. It is 0, K, H, M, 2. Well, and this operator is just a derivative with respect to the parameter. Yes. H0 and H1 are formal parameters. Theta with these indexes are one forms. Alpha 0, alpha 1 are one forms. And using this equation, we see that the first cohomology group of this algebra, let it be, well, this equation is E, and this system is the structure equations for this symmetry algebra. Then the first cohomology group is generated by alpha 0, and the second twisted cohomology group is either one-dimensional when the parameter C is 1, or it is 0 otherwise. So
you write already the default cohomology.
yes, the twisted second cohomology of this symmetry algebra, of this algebra, is one-dimensional when C, when this parameter is equal to 1. So from this fact, it follows that equation of the form d tau is equal to alpha C is 1, so alpha multiplied by 1 multiplied by this tau plus this deformed cocycle, twisted cocycle. This equation is compatible with the structure equations of our symmetry algebra. Well, all the forms are known. All the forms are known. Okay. They have the following form. Alpha is some dq, alpha 1 is minus ds, theta 0, 0, the so-called basic horizontal forms is this form, theta 1, 0 is this form, okay. Theta is 2, 0 is something like this plus something, and theta 3, 0, the form of this is the contact. Well, using this information, we can integrate this equation and obtain tau. And tau turns out to have the following form. It is E the degree Q, this Q, dV minus Q ds. Well, this was the first step for constructing the Lex representation of our equation using this technique. Then the second step. Now we say
so this Q is not the Q that you used in definition of Lux.
Oh, yeah, sorry.
This will be
V. This is just a formal parameter that governs the change of this form. Okay, now we say that by the very definition of the cohomology group of cohomology groups, if we add some linear combination of Maurer-Cartan forms of all the forms of from the structure equations, we obtain the twisted cycle 2. And now we try to search a linear combination of this form only with basic horizontal forms. So tau minus c, say, sum for k from 0 to 2, c k theta k0. And well, we say that this form, we put this form equal to 0, obtain the system of PDEs for the this variable v, and can consider what is this system for which choice of this constants the obtained system is Lax representation for the initial equation. It turns out, first we without loss of generality, we can put C2 equal to 1, because otherwise we just rename parameters. Well, and then it turns out that we have only two choices, two possibilities. When C0 and C1 are equal to 0, we obtain exactly the Lax representation found by Mikhailov, Pavlov, and Dunaysky. This Lax representation. Well, S, which appears, this S, turns out to be, well, in this picture, turns out to be a non-removable parameter of the Lax representation. Well, once again, this Lax representation was found independently by Mikhailov, Pavlov, and Dunaysky. Well, but there is another choice of these parameters. If C1 is equal to C0 is equal to C1 and both are equal to 1, then there is another Lax representation. It looks like so this one. This from this Lax representation, which is not equivalent to this Lax representation. Well, it was found this year. Well, the system depends, the V depends on 4 variables, while the initial equation depends on 3. But it is possible to check and show that the condition that US is equal to 0 is encoded using in these formulas.
The first equation, there is no x.
Oh, sorry. Thank you. Okay, this example emphasizes the following: that two consequential steps in the analysis. First, we find the twisted extension. Then the next step is to analyze the possible forms of Lax representations.
But what is Lax representation? Because this is very nonlinear.
Yes, but well, yeah, and so yes, it is unlinear. What is an example of? Well, okay, differential covering is it okay? Differential.
Any equation for which compatibility condition gives our equation.
Any system of equations, yes. If and only if this equation, this system is compatible if and only if this is satisfied, this condition. Yes.
You cannot get rid of this differentiation along S.
Yes,
You can?
I can. Actually, the equation that will appear is contact equivalent to initial equation. The dependence of U with respect to S can be eliminated by a contact transformation. Well, I have shown this example a year ago, actually. Okay, it's just to repeat the technique and to emphasize that this stage, the second step, is important.
Yes.
Okay, now once again, unfortunately, this technique is not universal. There are examples that, well, I can't recover the Lax representation for some equations using this technique. And the aim is to generalize the technique by means of the.
For example.
There will be example.
There will be.
For sure, okay. Well, so now I would like to discuss Lie-Rinehart algebras. Well, this, actually, this say construction was well known to Elie Cartan. His paper of 1904 contains all the formulas that are included in the notion of Lie-Rinehart algebras. But we'll say explicitly, this definition was given by Hertz in this year, and Hertz called them Lie pseudo-algebras. Then they were examined by Palais. And he called them Lie rings. Then they were studied by Rinehart. And actually, Rinehart emphasizes that his construction is the same as Lie pseudo-algebras. but nowadays they are called Lie-Rinehart algebras, while there is a survey by Mackenzie and he notes that there is at least 16 different definitions, different names for this object. At least 16 here. Okay, now what are these Lie-Rinehart algebras? Let R be a commutative ring. A script, let be a commutative algebra over this ring. And let G fracture small be a Lie algebra over this ring. Well, suppose there are defined two structures, defined two maps. The first, the structure of left A module on this Lie algebra. So there is a map, then the product over R to this Lie algebra. It takes the tensor product of element from A and element from the Lie algebra and maps it to an element of the Lie algebra. Well, and let it be denoted by this way, the lower dot. This is the this map defines the structure of A module. So if we take two elements of our Lie algebra, okay, then we obtain the following. Oops, sorry. The second structure is a map from the Lie algebra to the Lie algebra of derivations of commutative algebra A script. And this map is called anchor. And the requirement is the following. This map is the same simultaneously a morphism of Lie algebras, a homomorphism of Lie algebras over the ring. So A of commutator is commutator of images, and this A is a homomorphism of A modules. So if we act by an element of this form, we obtain the same as we take and apply to B. X Y are elements of the algebra, A, B are elements of the commutative algebra A. And we say that this Lie algebra is called a Lie-Rinehart algebra if Lie-Rinehart algebra if the following compatibility condition is satisfied. If commutator of X and the following element, we multiply Y by A, and the result of this commutator will be the following: plus A X of A acting by Y. Okay, if so, we say that this Lie algebra is the geometric counterpart of this algebraic construction is Lie algebroid.
A bit more general, but yes.
Survey by Mackenzie, written by Mackenzie, discusses the interrelations of these definitions.
For the algebroid, there is a second definition through vector field, which where is zero. Is there here another definition?
Well, I'd like to, this discussion. You may check the survey by Mackenzie. Well, in my talk, this definition, actually, some very special case of the definition, but I'd like to use this. Okay, now notation. I will use the following notation. I will use the following notation. This object will be denoted in this way: Lie algebra and the commutative algebra. Since both will be changed, yes, will be this Lie algebra will be extended and this algebra will be extended. So more or less natural to denote them in this way. Okay, now a Lie-Rinehart module over a Lie-Rinehart algebra. A Lie-Rinehart module over a Lie-Rinehart algebra is a vector space be capital such that the vector space equipped with two operations. Refers on two maps. Okay. Well, instead of this long notation, a anchor of X acting on A small, it will be used this notation: X acts on A small. here it is. Well, and the second operation, multiplication by elements of A script. Sorry. Something. Okay. Such that first map makes V into a Lie algebra model. So is the first map makes the space into the Lie algebra model. The second map makes it to be A algebra, the commutative algebra A model. Well, and additionally, there hold two conditions. The first one, if we apply A acts on X, then the result acts on V. It is the same as A applied to X of V. And if X acts on A applied to V, the result will be the following. A multiplied by, acts on X of V plus, well, let me X of A applied to V. Okay, one model for each Lie-Rinehart algebra, one model, namely the commutative algebra A itself, is applied in the natural way. So, example, A itself is a Lie-Rinehart model over the Lie-Rinehart algebra GDEq. Well, and the first map is X acting on A, anchor actually, and the second map is just multiplication in the A script algebra. Okay, now we have algebras, we have models. We can define cochains and cocycles, boundaries, and so on. We can define cohomology groups of a Lie-Rinehart algebra with coefficients and in a Lie-Rinehart model. So now we have a Lie-Rinehart algebra. V capital Lie-Rinehart model over this algebra. Well, then define cochains of dimension 1. Of our Lie algebra with coefficients and V, just as V itself. And cochains of dimension n as skew symmetric maps morphism over A to V. Well, and define differential by the Chevalier-Lenberg formula. So then, well, the square of this differential is equal to 0. So there are defined homology groups in usual way.
So lambda of this kind is external
Yeah.
power of G with coefficients.
Yeah. Okay. So there appear cohomology groups referred to as the cohomology groups of our algebra, our Lie-Rinehart algebra with coefficients in the model. Well, what are cohomology groups with trivial coefficients in this approach? More or less natural to define cohomology groups, to consider these cohomology groups as well, cohomology groups with trivial coefficients. So let for short, when A is fixed, they will be denoted in this way. For short, just for short, not to write this long collection of symbols. Well, now consider the particular case of this construction. In all examples below, the ring R, it will be the field of real numbers. The algebra A, the commutative algebra A, it will be algebra of functions on some n-dimensional space. So there will be functions of variables, say W1, Wn. And in all examples below, the Lie algebra G will have basis a countable basis. So actually, as this Lie-Rinehart algebra as a model is free. Well, the elements of this Lie algebra will be finite combinations of the following form. Functions of these W's multiplied by elements of this basis, and all the sums will be finite. Then what is the anchor? The anchor will be defined if we write sorry, element of a base. If we define how element Vi acts on the variable Wq. It is a certain function, some function of this W. Okay, this is anchor. Now conditions. there are two requirements. This space should be a Lie algebra, and well, the anchor will be should be compatible with the structure of Lie algebra. So we take two elements of this basis, and they should be a linear combination now with coefficients. Coefficients are functions of W of elements of this basis. And now we say, since this is a Lie algebra, there should be cyclic sum this cyclic sum should be equal to 0. So these coefficients must satisfy the following equation. Okay. GK multiplied by the partial. Okay. HQI multiplied by the partial derivative of the structure function CMJK with respect to WQ plus CLJK CMLI. This cyclic sum should be equal to 0. Well, and these are functions of the W. And the compatibility of anchor. So it should be fulfilled the following requirement. It should be CKIJ of W. Okay, so we can, the functions H, functions that define the anchor, are not arbitrary. They should satisfy the following conditions. HSI applied by the partial derivative. This partial derivative minus this should be CKIG. Okay.
Don't understand.
Yeah.
So our anchor is actually representations of the Lie algebra G as derivations of A. Now, in this case, as vector fields.
Yeah.
Yes.
Derivation.
But to express this property, we must know structure constants of G, and
they are not actually not constants but functions.
But for G they are constants.
Well, we have a basis, yes. We have no reasons to believe that this is the combination is with constants.
Yes, of course, this is correct. But how these functions C, I, J, K now take a basis in G, yes?
Yes.
We shall have
Compute
some constants
No.
in G.
No.
G is an real algebra over real. G.
Excuse me, can I comment?
Yes, of course.
I think I can answer your question. You are talking about different structures. So G is a vector space over R, right? But the speaker is, but it is also a free module over the ring A. So the speaker is talking about a basis of the free module G, not of the vector space G.
I understand, Senor. I understand this.
So indeed, then the structure constants are of course functions and not constants. So you have all the G admits also an infinite basis over R, but it is not considered in the talk. This infinite, it is much bigger and is not considered in the talk.
But anchor is a map that takes elements of G to derivations to vector fields.
Right.
Yes. So this anchor should be should reflect compatibility of.
It is a homomorphism of Lie algebras, right?
Yes. So where are
Lie-
structure constants of G? Because
They are not needed. The classical structure constants, which are constants, they are not needed because it is sufficient to consider G as a free module, not as a vector space. So G has some basis as a vector space, but it is not needed and is not considered.
But where do I see compatibility of the bracket in G of the bracket of vector fields? That's what I want to understand.
Compatibility of what?
Again, we have two Lie algebra structures in G and in the algebra of vector fields. And the anchor should be compatible with one and the other. So I do not see this compatibility. No.
Once again, moment.
Our anchor takes elements of G to derivations of the telegraphic A. Yes.
Yeah.
Derivations of the telegraphic A is actually vector fields on Rn. Yes. So
if A is yes, vector fields, they are given by the formula. I'll say.
Again, what is the property? How the property of anchor reflects the bracket in G?
How
The definition of Lie-Rinehart algebra. What is
the proper properties? First, we say what? We say if what? If well, if we multiply this by a function. It's no problem. Yeah. No problem. But well, the next question is what? How to apply this to an element of A.
Commutator in G.
Commutator in G.
Apply anchor to it.
Apply anchor.
Yes. No.
Now apply this to WQ. Yes, it is, well, differentiation in. So it is just this commutator. where this action, well, okay. Vi, Vj act on Wq minus
No.
define.
Where is
But we say that but this is the same as sum C Vk. Apply and act. Well, and this will be Ij multiplied by this. Okay. Q K W S equals certain or in terms of this coefficient. Okay, now what? Okay, well, now take consider sorry. Okay. Consider a linear function let them be theta I from our algebra to R defined as follows. They are dual to the vector, to the basis of our algebra. Then define differential in accordance with the Chevalier-Lemberg formula. It will be of the following form. And well, the anchor, or it can be written and the anchor GDEq is sum HQI theta I. And it is not hard to check directly.
Excuse me, can I ask something? Theta I, maybe theta I is it will be a differential form, right? Sort of differential form. Don't maybe maybe it is a map to A, not to R, but to A, to the algebra A, probably.
Okay, you are quite right. Okay.
Right. Thank you. Yes.
Okay. Thank you. Okay. Well, then the square of this differential will be 0 if and only if the equations, the requirements for functions C and H are satisfied. So this system is referred to as the structure equations of our Lie-Rinehart algebra. Okay. Remark. The structure equations of Lie pseudogroups are a particular case of these structure equations. the second remark. In all examples below, the sums for the anchor will be considered, will be finite. Sums will be finite. So it's the additional requirement. As it is in the case of Lie groups. Therefore, in this situation, when all the sums are finite, we, without any loss of generality, can consider that the rank of this matrix is equal to Q, to the number of variables W. Otherwise, we can reduce the number of this W. Otherwise, if the rank is less, we say that some W's are functions of other.
How can it be? Q is just
W's, well, so W is function of multiplied by theta 1, another function multiplied by the same theta 1. So actually, say W2 is some function of W1. And we can reduce the number. If we suppose that W's are independent, we can consider that rank is maximum.
this G and so are H, yes?
Yeah.
But this is diagonal.
Then we say, then there is a functional dependence between them. Suppose H1 is not 0. Then what? H2 multiplied by H1. We have an ordinary differential equation. And we solve it with respect to W2 and say that W is some function phi of W1. If the number of, theta 1. If so, we say that actually there is a functional dependence between these W's. So, in other words, we can rename the forms.
I это матрица.
Yes. Yeah. The number of columns. So I'm awfully sorry. It is n. The number. I'm awfully sorry. The number of this.
This finite number.
Yeah, I'm awfully sorry. It's just the number of this W. I'm sorry. So we can rename. We consider new one forms at Q equal to the sums. And then we say dwq is eta q, and so d eta q should be equal to 0. Well, so rename the forms that are included in the right-hand sides of the anchor. We now call them eta. And all other will be theta again. Theta 1, and so on. Theta n, and so on. Then the structure equations can be written in the following form. Well, this part, and the structure equations for thetas. Okay. Just C capital I J K W theta J K plus some functions theta I eta Q plus Q I Q S W theta Q theta S. Well, these constants are skew symmetric with respect to J and Q, and these functions skew symmetric. Oh, sorry. Well, the structure equations can be written in this form. Actually, these functions can be constants, but well, the fact that it is not a Lie algebra is encoded in this part. Okay, now we can define the twisted extension of a Lie-Rinehart algebra. How many minutes have I now? Okay. So now suppose that the first cohomology group of our Lie-Rinehart algebra is not 0, and there is a function alpha, one form, sorry, alpha, such that its differential is equal to 0, but alpha is not a differential of any function. So alpha does not belong to the with trivial in the sense that we have discussed. Okay, then for a number, for a constant, not a function, but a constant, we define the twisted differential let lambda be a constant, not a function. Then define twisted differential of some one form omega as usual differential minus this expression. Then we say, since alpha is closed and since lambda is constant, the square of this twisted differential is equal to 0. So there are defined the twisted cohomology groups, and well, we denote them. Well, of the interest will be the second cohomology group, and it will be denoted well in full in this way. So now suppose that the form omega capital defines an element of this cohomology group for some fixed lambda 0. This cohomology group is non-trivial for some lambda 0. Fixed constant. Then, well, define. So, in other words, d omega is lambda 0 alpha multiplied by omega. Then define new equation for unspecified one form tau. Consider the following equation. Oh, sorry. The same as in the situation as for Lie algebras. Well, we say this equation is compatible with the structure equations for our Lie-Rinehart algebra, so it defines new Lie-Rinehart algebra. Well, and this extension will be called twisted extension for the Lie-Rinehart algebra. In this moment, the definition is the same. So we have this algebra with non-trivial second deforming cohomology group for some lambda 0, and we construct new with the same algebra A. Algebra A was not changed. Now we have another. Well, let me consider an example. An example. Consider the following Lie-Rinehart algebra. The Lie-Rinehart algebra with the following structure equations. Something wrong. And d eta is equal to 0, and eta itself is differential of invariant W's, only invariant W. Then the first cohomology group is generated by this alpha. The second cohomology group is either one-dimensional. Sorry. C alpha 0. Alpha, just alpha. Is either generated by this cycle when C is equal to 2. Or it is two-dimensional. When C is equal to 1, or it is 0 when C is not 1 or 2. This algebra will be a part of the further example. It is a part of symmetry algebra of one equation that will be considered if the time. Well, so this part, this part looks like a Lie algebra if we have known this. So it's just Lie algebra, but there is another equation. So this form actually is exact. This one form is exact. It is a differential of some invariant. While the coefficients of this Lie-Rinehart algebra are constants, all of them are constants, the twisted extension has a cycle whose coefficients do depend on this invariant. That is specific for Lie-Rinehart algebras. So we can extend our Lie-Rinehart algebra, this structure equations, we can define 3 more equations. Okay. Something wrong. Okay. Alpha lambda plus alpha theta 1. This corresponds to this cycle. D tau 2 alpha tau 2 plus W alpha plus alpha multiplied W theta 1 plus W theta 2. And the third equation corresponds to this cycle, and C is equal to 2. So this is 2 alpha multiplied by tau 3 plus theta 1 multiplied by theta 2. So this cohomology group defines 3-dimensional twisted extension of our Lie.
Which case do we consider? C
equal to 2. Here it is.
and
C equal to 1, C equal to 1. Oh, sorry. Yeah, everything is correct. Correct, and this is correct. This cycle tau 1, this cycle defines tau 2, and this defines tau 3. Tau 3, okay.
Tau 2, yeah, 2, okay.
So this cohomology group defines 3-dimensional twisted extension of our Lie algebra. Now, actually, we have another way to extend a Lie-Rinehart algebra with non-trivial first cohomology group. We can kill this cohomology group. So if alpha is an element, is non-trivial element of the first cohomology group of our Lie-Rinehart algebra with trivial coefficients. Now we extend the algebra A. We define new element, let it be, say, W0, such that dW0 is equal to alpha. So now we extend the A part. The A part. We kill this element of the first cohomology group by appending new zero chain. Well, and actually we can apply for if our Lie-Rinehart algebra has non-trivial first cohomology group, we can apply both extensions. First, we construct twisted extension, and after kill the first cohomology using this procedure of appending invariants. So, let it be say double twisted extension, or I don't know how to call this. Some ungrateful extension. If we use alpha to extend, to construct twisted extension, and then kill it. Oh.
Eventually, we consider both extensions. Both for at first we take twisted extension, since otherwise, when we use the second extension, the twisted extension has no sense. It is not a twisted extension. This double twisted extension, is not a twisted extension. So it is what do we consider?
One
Double extension or no?
Once again, we have Lie-Rinehart algebra, and its first cohomology is non-trivial. First, we extend the algebra using the procedure of twisted extension. Oh, sorry. Twisted extension. And then extend the ape.
So we first extend
Algebra,
and then
and it will be 2 steps. The result is not a twisted extent, but some extent will. So in this example, we add some W0 such that. Okay. Well, now why we need these definitions? 15 minutes, yes? Is it correct?
Yes.
Okay, so just one example of applying this procedure for constructing Lax representations of differential equations. Consider the following equation. Here, f is a function of uxx, and this f is supposed to be a solution to Shazi ODE, Shazi ordinary differential equation. This equation was introduced by Maxim Pavlov in this year. In the next year, Maxim found a Lax representation for this equation, but his formulas are in implicit form. And in the paper by Zhenya Ferapontov and sorry. Oh, sorry. The Lax representation was given in explicit form. Well, now how to recover this result using the machinery based on Lie-Rinehart algebras. We find the structure equation for the symmetry. Let it be pseudo group of this equation. It turns out that the structure equations have the following form.
Before proceeding, just say a couple of words how symmetry algebras become Lie-Rinehart algebras.
Yes, it is the purpose.
So without structural.
Because they have invariance. For example, this equation has the following invariant. This function is invariant with respect to any derivative, any symmetry of this equation.
Okay, and what?
And
So what is the finite dimension of the algebra, and what is our anchor, and what is our?
Yeah, well,
without structure equations, just.
I can't. Well, the formulas are too long to be written without structure equations. While with
No. We take PDE. We compute its symmetry algebra.
Yes.
So then, where do I look for Lie-Rinehart structure? Or you see them only in specific examples?
Well, I see them when I write explicitly the structure equations of symmetry pseudogroups, because these equations, the coefficients are either constants or invariants. If there are functions, if the coefficients are functions, and I can't write it with constant coefficients, you say, oh, okay, this is invariance. Then I check without any structure equations, it is possible to check that this function is invariant with respect to any symmetry of this equation. But well, I found it when I write explicitly structure equations.
Excuse me, can I ask something?
Yes.
I think, do you need to compute all symmetries? Maybe you need just some algebra of symmetries, not all of them. Just you consider some specific algebra of symmetries of this equation and find Lie-Rinehart structure on it. It is not necessary in principle to compute all symmetries, probably, right?
Perhaps, but well,
because
I find all of them because I need to know the structure of this Lie algebra, and then I'll try to find twisted cohomology and so on. And for this purpose, I need the structure equations.
Right. So, but do you really compute all symmetries? You have a proof that your Lie-Rinehart algebra contains really all symmetries of this equation?
I don't understand your question.
Well,
I have a question.
Not a very important question. Okay, you can proceed.
Thank you. Well, so the structure equations for the symmetry algebra of this equation can be written in the following form. First part is the structure equations from the above example. Yes. For some mysterious reasons, the notation is different, but well, I don't know why. For some mistake. Okay, this is eta. Sorry, this is the only difference. No. Okay. And actually, this part and dw is eta, where w actually is this uxx. This is the structure equations from the previous.
Again, what is our Lie algebra in this moment? This is a finite dimensional.
No. And then a huge infinite dimensional ideal. Which actually this part is not interesting because it turns out that twisted extension is generated by this part, but it is well a posteriori. At the first, we can't expect that the infinite dimensional part is not interesting for the further constructions. Okay, and we know all the forms. We know all the forms explicitly. We know that eta is dux x. We know what? We know that alpha 0 alpha 0, please alpha 0. Now it is something like this. Alpha 1 a dx and so on the basic horizontal forms dt set 1 0 a uxy dy plus utx minus 2 gt and so on.
Oleg, what is our A here?
What is our the anchor? Sorry.
Relation for our object with the algebra, and it's roughly speaking representation of the relations of some commutative algebra. So the algebra is
The algebra
of functions in UXX.
Yes.
So this is our A. Yes.
Yes. And this object has the following structure. There are some expressions that are not interesting right now. So now we say, but the previous example tells us that there is a twisted extension for this construction. We say we can add, and actually we need only what? We need only tau 2 from the above expressions, from the previous example. This tau 2 has the following form: a multiplied by dv plus logarithm a dx. V is the fiber variable of the future covering. And now what we say? Now we kill the cohomology. The first cohomology. This. We choose this A. How we proceed? How we proceed? We say the following. We consider the linear combination. Sorry. No. Page 15. Oh, here it is. We consider the linear combination. This tau 2. And then what? Some function, let it be h capital, multiplied by theta 0, 0, the basic form that governs dt, minus h1, let it be h capital 2, theta 1, 0, this form that governs y. And actually x is included. Dx is included. We need no any other forms.
I'm sorry, and just this v is a new variable that is the second step of our extension.
No. The second step is A.
And
v is the integration constant when we find tau. This is the first step of our extension. When we find this tau, we integrate the equation d tau 2 is equal to alpha 0 plus. When we integrate, we obtain.
So up to eta, it was the first step. Yes.
Sorry.
So where the first step finished?
When we find this tau. Actually, it was finished in the previous example.
You define tau using A, and you said that A.
And then the first step is finished now here. But the second step we say, but now we say that A is new invariant. And now we are searching for this combination. And the question is, what are the arguments of these functions? Well, we say these functions are functions of what? Uxx and our A. This A. Then we substitute everything. And it's turned out that this linear combination is the following. Minus uxy h2 dy minus uxy 3 h1 plus h2 utx minus 2 fuy 3 dt. But we say this will be the Walkes-Testabrook form of our covering. So this should be what? Minus Vx. When take horizontalize this form, we say that. So A, actually this A is E in the degree minus Vx. So actually we can, instead of A, substitute Vx. Because well, just any function of this invariant. So we say these functions actually are functions of Uxx and Vx. So we substitute everything here and we obtain the following system. Vt is what? Vt, where it is? This one. Okay, and Vy is just this one. And then we say now we should analyze this system for compatibility. Actually, this system is exactly the system from the paper of Clary-Ferapontov. And the dependence on the invariance, the same in the dependence. Then analyze the system and obtain exactly this result. And we obtain an overdetermined system for these functions h1 and h2, and its compatibility conditions is fulfilled whenever this f, the function f from the initial example, is a solution to the Chauzy equation. So in other words, all the information about our equation is encoded in the structure equations for its Lie-Rinehart algebra, symmetry algebra.
But you should have two results, two different results, because the case is C equal to 1 and C equal to 2.
No. Those coefficients were for the hyper-CR equation of Einstein-Weil structures. No, the only one result. The first example is not about just recalling the technique. No. Here analysis gives only one solution. Exactly the solution found by Clary and Ferapontov. Well, once again, all the information, including the Chauzy equation, can be extracted from the structure equations of the symmetries of the symmetry algebra of of operation. These structure equations actually contains this form eta xx, and this prescribes dependence of H1 and H2 of this U xx, while the dependence of Vx is prescribed by the second step of extension of the Lie-Rinehart algebra when we kill the alpha zero, the form alpha zero. Kill as an element of the first cohomology group. So, perhaps I should stop.
Okay.
Thank you for your attention.
Give me please microphone. Okay, thanks a lot. Questions, remarks?
I have a remark. Can I say?
Yeah, sure.
Yeah. So Oleg, in the very beginning, you started with a PDE, then you considered some pseudo potentials for it, and you computed the compatibility condition, and you said that the compatibility condition coming from cross differentiation must be equivalent to the initial PDE, right?
Yeah.
Right. Actually, when you consider coverings in the standard definition of coverings of PDEs, the requirement is slightly different. The compatibility condition should hold as a consequence of the initial PDE, not necessarily equivalent to it, but it should be a consequence of the initial PDE. And in my opinion, this is better version. So in principle, you should consider Lex pairs where the compatibility condition is a consequence of the initial PDE, in my opinion.
Well, but actually, I don't know such examples.
There are such examples. For example, I think there are such examples. Well, we can discuss it.
Okay. Let's discuss it in a different meeting. Okay.
Yeah, right.
Thank you.
Okay, thank you. More questions, more remarks? Okay, then thanks a lot. It's not at the moment clear in which form the next session will be held. Maybe in combined form, maybe purely online, but it will be announced tomorrow. So thanks a lot and see you next Wednesday. Goodbye.
Goodbye.
Goodbye.